Now we have to go to the third and last postulate of our course, which is about evolution. Remember, it's very important we keep in mind the real difference between classical and quantum physics is at the level of the description of the physical system. In classical physics, states belong to a set. In quantum physics, states belong to a vector space. And this carries along all these probability issues that we have seen with the measurement, intrinsic randomness, and so on. Now, because we are working with a vector space, the dealing of time evolution, well, is also a little bit different, although again, not in a very essential way, from the way of Newton's equations of motion. Okay, so let me first write down the fundamental equation. So the time evolution of a closed quantum system is the famous Schrödinger equation. So let me write it down, maybe here. So closed quantum system, the state psi of t evolves according to the Schrödinger equation, that is I h bar time derivative of the state is h possibly of t psi of t. Here there are two things that you have not seen before. H bar is a constant at the level of axioms or postulates. We don't know the value. Of course, we know the value, right? Is the modified Planck constant h over 2 pi. The dimension is an action, so is energy. So joule, the units joules times second. The values 6.6 times 10 to the minus 34. This object is an operator, is the Hamilton operator, usually called Hamiltonian for simplicity. That is the object that generates the evolution. So the Hamiltonian does not describe the system, that's the space of state. It does not describe the properties of the system, that's the state. It describes the evolution, or more precisely, it's the operator that generates the evolution. In that sense, it plays the same role in Hamiltonian dynamics classically. Okay, so now, first of all, so this is the Schrödinger equation that we're going to spend a lot of time working on during the next chapters, especially chapters 4 and 5. Now, what do we have to say? First of all, we have to say that, I mean, to throw this equation to you and say, this is a postulate, it's not a very satisfactory situation. There is a slightly more satisfactory one, although I will not be able to do all the proofs from the postulate to here, but let's take as a postulate 3, that the evolution of a closed system is reversible and is described by a linear operator. Now, the fact that the evolution is reversible is exactly the same as in classical physics. Remember that in classical physics, ultimately, right, for a closed system that is true, and ultimately we also believe that even irreversible evolution are actually effective ones because we don't control all the degrees of freedom, right? But if we are able to control all the degrees of freedom, even every evolution will be reversible. That's a belief in classical physics as well. Now, why a linear operator? This is the part I cannot really justify. All kind of bad things happen if you don't have a linear operator. That's maybe the best thing I can say. And now, so this postulate implies that there is a kind of closed form for the psi of t. So this is a differential equation. This must be solved. In principle, there would be a closed form for the psi of t that is of this type. So there is an evolution operator that is unitary. So this is really, again, I cannot do the full proof, but this is, again, exactly a consequence of the fact that you want a linear operator and you want it to be reversible. Think about it with a hand-waving statement. An evolution is like a change of basis. That's what it means, right? So you could somehow fix your state and have your understanding of the state evolve rather than fixing your understanding of physical properties and move the state around. It would be the same, and that's what that's the consequence of being reversible. Now, sorry, I have to say that, of course, if there is no time evolution, so this unitary operator is such that u of t0, t0 is the identity, right? If you evolve for 0 time, well, you don't evolve. Okay, so now here I have, in the lecture notes, I will not do it here, I have a kind of derivation of the form of the Schrödinger equation. So by taking the derivative of this thing with respect to t, you would end up with something that looks like this, with the Hamiltonian related to the derivative of this operator. Now, instead of doing the general abstract explanation, let me go to a very important specific example, that is the example of time-independent Hamiltonians. So let's, this is a special but very important case. So solution of the Schrödinger equation for a time-independent H Hamiltonian. So here you are going to see that contrary to what happens generically in Newton's theory, essentially we are going to solve this differential equation in a canonical way, always the same, and the procedure is fixed. So you may say, well, then it's trivial, right? We can always solve the Schrödinger equation. Well, it's the first step that is not trivial. And now let me tell you what the first step is. So this, I'm going to write in red the step that is not easy, usually. The rest, if you manage to solve this step, the rest will be trivial, and I will show you how. So the step that is not easy is, let's assume that we have found what is called the diagonalization of H. So which means we have found the eigenvalues and eigenvectors. Let's assume that we have found these. Let me copy from the lecture notes. Now, for finite dimension, this is finding the eigenvalues and the eigenvectors of a finite matrix. It's in principle not unfeasible, at least with Mathematica or MATLAB. For infinite dimensions, this would be usually a nightmare. So this is the problem of solving the Schrödinger equation. But let's now assume we have done it. Okay? You may say, how comes that having the eigenvectors and eigenvalues of an operator help to solve a differential equation? That sounds a bit crazy, right? Okay, let's assume this, and let's see what we can do. I will erase these. So here I give you the recipe. Let's assume this, then recipe for full solution. Point number 1, write the initial state. Of course, you need to give an initial state, just as in a Newton equation. in the eigenbasis of H. So which means the psi at time 0, you write as sum over k, ck, k, where ck is equal to k psi over 0. In other words, you need to compute all the scalar products. And now this is your initial state. Now, I should have told you something before. I'm sorry for that. There is a kind of obvious observation that I should have made before, so that later I can give you the second part of the recipe. Let me do this observation here. If H now is not dependent on time, you may recognize what this formula looks like. I mean, if this were a number, you know the solution to this equation. It's an exponential, right? Time derivative of f d over dt of f is equal to alpha f implies f is equal to f0 e to the alpha t, right? That's the differential equation of an exponential. Now, as it turns out, this works also when this object is an operator. So from these, if H is time independent, that's the important thing, right? We have that psi of t is equal to e to the minus I h t over h bar. The I and h bar come from here. Psi of 0. This is the famous unitary operator, u of t. Okay? So we see that already if H is time independent, we have a formal solution for the Schrödinger equation. Now let me go back to the recipe. If in addition I have this is a function of H, a function of a Hermitian operator, then second part of the recipe, u of t, well, is equal to what? Is equal to sum over k e to the minus I e k t over h bar k k. Remember, what I've used here is that the function of an operator f of A is equal to sum over k f of the eigenvalues with the same eigenvectors. Here are the eigenvalues of H. Here is the function I have to compute. Okay? Now put the two together. I have that, where do I write it? Maybe I write it here. Here on the top. Point number 3, so therefore, psi of t is equal to u of t psi of 0. Well, we have both. We have psi of 0 in this basis, u of t in this basis. If you don't see it, take your time to see it. This will be sum over k, ck e to the minus I e k t over h bar k. And this is a kind of ck of t. And this is the final state. That's it. We have the state that is the time evolution starting with psi of 0. So that's all. I hope you appreciate how here solving an eigenvalue equation leads you to solve a differential equation. So this recipe is a recipe that you have to learn by heart. It will definitely appear in some test, in some exam, somewhere. I can't let go this, right? This is one of the most fundamental computational tools in quantum theory. So remember, the assumption is that the H is time independent. If the H is time independent, you write H in its eigenvalue and eigenvector. That's maybe the difficult part. If you're able to do this, the evolution is automatic. Okay? Now, what happens if H is not time independent? Okay, this is again something we leave for QM2. Apart from one small example that you will see in the next chapter, that I will do a bit hand waving, because again, in the lecture notes it will be done very well, but I don't have time to go into these things. Okay, the last point I want to make, this is a bit abstract. I will do it very fast. It's in the lecture notes, and it might come handy at some point of your life, is the same thing I did for probabilities, right? I always told you that the state is actually represented by projectors, not by vectors. Here is everything about vectors. How does it look for projectors? Well, you can demonstrate. So if I try to do the evolution of a projector, right, with projectors, well, first of all, the projector, the formal solution looks something like this. Sorry, U. Dagger. So, well, essentially, you say, wow, why there are two U's? Well, I mean, come on, this is psi, right? The evolution of psi is U, so this one, there's nothing mysterious there, right? So the psi evolves with U, the bra psi evolves with U dagger, and the projector will evolve again with U dagger, right? And the differential version of this is called the von Neumann equation, which is I h bar d over dt of the projector is the commutator with the Hamiltonian of the projector. Again, this is exactly this when written with a projector. And now, just the last thing I want to mention is that with this thing, with this trick, you could move to what is called the Heisenberg picture, which is something that we may not need in this class, apart from a remark I will make at some point, but it might be useful in the future, so just as well mention it here. So it's very qualitative what I'm going to do. So the state evolves. This is called the Schrödinger picture, I think we call it, yes. Now, you could adapt a different strategy. You can say, well, the state is fixed, but it's the physical operators that evolve. The definition of the physical operator evolve in time. It can be useful for some calculations sometimes. So the physical quantities evolve, so the operators, this is called the Heisenberg picture. It gives the same result, obviously. And so you may say, well, if an operator evolves, how does it evolve? Well, more or less like this, but the dagger is on the other side. So the evolution of the operator A in Heisenberg picture would be something like that. U dagger U, and the differential version is the same as here, but with the commutator reversed. So you put first the operator and then the Hamiltonian. Okay, you will see later, probably in chapter 4, I will discuss a case where this comes handy. For the moment, let's leave it here. And with this, we finish chapter 2. And next time, we are going to discuss chapter 3. You can stop.